Welcome to my channel. Today, we're going to discuss decision trees, one of the most fundamental and intuitive algorithms in machine learning. Decision trees are supervised learning models that work by asking a series of questions to make predictions. Think of it like a flowchart where each question leads you down a different path until you reach a final answer. As we explore this concept, you'll see a beautiful tree structure gradually taking shape. The tree grows branch by branch, with the root node at the top representing our first question. Data points flow into the tree from the left side, each one following its own path through the branches based on how it answers each question. Eventually, every data point lands in a leaf node at the bottom, which gives us our final prediction. The colors on the leaves tell us which class each data point belongs to. What makes decision trees so powerful is their simplicity and interpretability. Unlike black box models, you can actually trace exactly why a decision tree made a particular prediction. This is incredibly valuable in fields like healthcare and finance, where you need to explain your model's reasoning. The supervised learning badge you see reminds us that decision trees learn from labeled training data, using examples where we already know the correct answer to build their decision rules. Now let's build some intuition about how decision trees actually work. The core idea is surprisingly simple. Decision trees make predictions by asking a series of yes or no questions. It's exactly like playing the game 20 questions, where each answer eliminates certain possibilities. Imagine you have a mixed basket of fruits, some apples and some oranges, and you need to sort them. The decision tree might ask its first question, is it red? This single question immediately splits your data into two groups. The red fruits go to the left bucket, and the non-red fruits go to the right bucket. Notice how the fruits smoothly animate into their respective buckets. What's beautiful about this process is that each split makes our groups more pure. Before the split, we had a messy mix of apples and oranges. After asking about color, the left bucket contains mostly apples, and the right bucket contains mostly oranges. If needed, we could ask another question like, is it round, to further separate any remaining mixed items. The key insight here is that decision trees are greedy algorithms. At each step, they find the single best question to ask that creates the purest possible split. They don't plan multiple steps ahead, they just make the best decision at each moment. This metaphor of sorting items into buckets using simple questions is exactly what happens when a decision tree classifies data in the real world. Let's break down the anatomy of a decision tree so you understand every component. A decision tree has four main parts that work together to make predictions. First, at the very top, we have the root node. This is where everything starts, marked with an orange highlight and labeled clearly. The root node contains the first and most important question, the one that best separates your data. It's called the root because, like a real tree, everything branches out from here. Next, we have internal nodes, shown in pink. These are the decision points in the middle of the tree. Each internal node asks a question about a specific feature, like is the income greater than 50,000, or is the education level above high school? When data flows through an internal node, it gets directed left or right based on the answer. Connecting all these nodes are the branches, highlighted in green. Branches represent the outcomes of each decision, typically yes on one side and no on the other. Think of them as pathways that guide data through the tree. Finally, at the bottom, we have leaf nodes, shown as green ovals. Leaf nodes are where predictions happen. They don't ask any more questions, instead they simply output a class label or a value. Every path through the tree ends at a leaf node. On the side, you can see a depth meter showing how many levels deep our tree goes. The depth is simply the length of the longest path from the root to any leaf. This is an important concept we'll revisit when discussing overfitting. Now let's understand how a decision tree finds the best way to split data. This is the heart of the algorithm. Imagine you have a scatter plot with two classes of data points, orange and green. Your goal is to find a vertical or horizontal line that best separates these classes. The algorithm starts by trying different positions for this split line. Watch as the dashed line moves across the plot from left to right. At each position, we calculate a quality score that measures how well this split separates the classes. The score updates in real time as the line moves. A higher score means a better split. The algorithm tries every possible feature and every possible threshold value for that feature. For continuous features like age or income, it considers all unique values as potential split points. For categorical features, it considers different groupings of categories. When the split quality score reaches its maximum, we've found our best split point. The line turns solid green to indicate this is the optimal position. The data naturally separates into two distinct regions, with orange points on one side and green points on the other. This process is called greedy optimization because at each node, the algorithm simply picks whatever split gives the best immediate improvement. It doesn't look ahead to see if a different split might lead to better results several steps down the line. This greedy approach is computationally efficient, but can sometimes miss the globally optimal tree structure. Let's talk about Gini impurity, one of the two main metrics used to measure how good a split is. The formula is elegantly simple. Gini equals 1 minus the sum of squared class probabilities. But what does this actually mean? Think of impurity as measuring how mixed a node is. Imagine you have a jar full of marbles. If all the marbles are the same color, like all orange marbles in our pure node example, then the jar is perfectly pure. In this case, Gini impurity equals 0. The probability of picking an orange marble is 100%, so 1 minus 1 squared equals 0. Now look at the mixed node, where we have equal numbers of orange and green marbles. This is the most impure state possible. The probability of each class is 50%, so Gini equals 1 minus 0.5 squared minus 0.5 squared, which gives us 0.5. The bar charts below each jar show the class proportions visually. A pure node has a single solid bar, while the mixed node shows an even split between colors. When building a decision tree, we want to create splits that result in the purest possible child nodes. The algorithm calculates the weighted average Gini impurity of the children and compares it to the parents' impurity. The split that reduces impurity the most wins. This is why Gini impurity is sometimes called Gini gain when we're measuring improvement. The key insight is that Gini equals 0 means we have a perfect classification with no uncertainty. Now, let's explore entropy and information gain, the alternative to Gini impurity that comes from information theory. The entropy formula is H equals negative sum of P times log base 2 of P, where P represents the probability of each class. Entropy measures disorder or randomness in a system. High entropy means high disorder, like a chaotic mix of particles bouncing around randomly. The visual shows these chaotic particles moving unpredictably in all directions. This represents a node with an equal mix of classes where we have maximum uncertainty about the outcome. Low entropy, on the other hand, means order and predictability. The organized particles are neatly arranged, representing a node where almost all samples belong to the same class. We can predict the outcome with high confidence. The entropy meter below each visualization shows the numerical value, with high entropy near 1.0 and low entropy near 0. Information gain measures how much entropy decreases after a split. It's calculated as the parent's entropy minus the weighted average entropy of the children. The calculation, step by step, shows we start with parent entropy of 1.0, make a split, and end up with children having total weighted entropy of 0.4, giving us an information gain of 0.6. This is significant because a gain of 0.6 means our split removed 60% of the uncertainty. We always choose the split that maximizes information gain, which is equivalent to minimizing the remaining entropy in the children. Let's walk through the complete process of building a decision tree step by step. This is a recursive algorithm, meaning it repeats the same process at each level. Step 1 is starting with all your training data in the root node. You can see we begin with 100 samples containing a mix of classes. This initial node represents our entire dataset before any splitting. Step 2 is finding the best split. The algorithm evaluates every feature and every possible threshold, calculating the impurity reduction for each potential split. The feature highlight shows that age was selected as the best feature to split on first because it provides the greatest reduction in impurity. Step 3 is creating child nodes. The data flows down the branches based on whether each sample satisfies the split condition. Samples with age less than or equal to 30 go left, containing 60 samples. Samples with age greater than 30 go right, containing 40 samples. Step 4 is recursing on the left child. We repeat the same process. Find the best split for just this subset of data. The algorithm selects income as the best splitting feature for the left branch, creating 2 more child nodes. Step 5 is recursing on the right child. Similarly, we find the best split for the right subset using score as the splitting feature. The tree continues growing until we hit a stopping criterion. The badge at the bottom shows our stopping conditions. Either we reach pure nodes where all samples belong to the same class, or we hit the maximum allowed depth. Other stopping criteria include minimum samples required to split or minimum samples required in a leaf node. Overfitting is one of the most important concepts to understand when working with decision trees. Let's compare 3 scenarios. First, we have a shallow tree with depth equals 1. This tree is too simple. It only asks one question, so its decision boundary is essentially a single straight line. This leads to underfitting, where the model is too rigid to capture the underlying patterns in the data. It has high bias but low variance. Next, we have an optimal tree with depth around 3 to 5. This tree asks enough questions to capture the important patterns without memorizing noise. The badge shows just right because this tree generalizes well to new, unseen data. Finally, we have a deep tree with depth 20 or more. This tree keeps splitting until every leaf contains just 1 or 2 samples. It perfectly fits the training data, achieving near zero training error, but it has memorized the noise and specific quirks of that particular dataset. This is overfitting, indicated by high variance but low bias. The graph below shows this clearly. The green line represents training error, which keeps decreasing as the tree gets deeper. The orange line represents validation error on held-out data. Notice how validation error initially decreases but then starts increasing after a certain depth. The point where the validation error is lowest is our optimal depth. The divergence between training and validation error is the classic sign of overfitting. This is why we never let decision trees grow unconstrained. We need to find that sweet spot where the model is complex enough to learn but simple enough to generalize. Pruning is the solution to overfitting in decision trees. Think of it like a gardener trimming a tree to help it grow better. There are 2 main approaches. Pre-pruning, also called early stopping, prevents the tree from growing too large in the first place. Instead of growing the full tree and then cutting it back, we set constraints that stop growth early. The visual shows a tree that stopped growing before it could create additional branches. Look at the dashed lines representing branches that were never created. The common pre-pruning parameters include max depth, which limits how deep the tree can grow. If you set max depth to 3, the tree will never have more than 3 levels of questions. Min sample split specifies the minimum number of samples required to split a node. If a node has fewer samples than this threshold, it becomes a leaf. Min samples leaf ensures every leaf node has at least a certain number of samples, preventing leaves with just 1 or 2 data points. Post-pruning takes the opposite approach. We first grow the complete tree, letting it overfit the training data, then we cut back unnecessary branches. Watch the scissors animation cutting through the branches. The algorithm evaluates whether removing a subtree improves performance on validation data. If removing a branch doesn't hurt accuracy, that branch was probably just fitting noise. The cost-complexity pruning formula shown at the bottom balances the tree's error against its complexity. The alpha parameter controls this trade-off. A higher alpha means more aggressive pruning, resulting in simpler trees. One of the most valuable outputs of a decision tree is feature importance. This tells us which features contribute most to the model's predictions. Looking at the tree structure, you can see different features used at different levels. Age is used at the root node, the most important position. Income and score are used at internal nodes below. The importance of a feature is calculated based on how much it reduces impurity across all the splits where it's used. Features used at higher levels of the tree and features used in nodes with more samples contribute more to the total importance. The bar chart shows importance scores for each feature. Age has the highest importance at 0.42, meaning it accounts for 42% of the total impurity reduction. Income comes second at 0.28, followed by credit score at 0.18 and experience at 0.12. Notice how the bars animate to fill proportionally, giving you a visual sense of relative importance. These scores always sum to 1.0 across all features. Feature importance has several practical applications. For feature selection, you can drop low-importance features to simplify your model and reduce training time. For model interpretability, you can explain to stakeholders which factors drive predictions. For dimensionality reduction, you can focus on the most predictive features when dealing with high-dimensional data. Remember that feature importance in decision trees is based on impurity reduction, which can sometimes be biased toward high cardinality features that have more potential split points. Now let's extend our knowledge to random forests, one of the most powerful and widely used machine learning algorithms. A random forest is simply an ensemble of many decision trees working together. The key insight is that while a single decision tree can be unstable and prone to overfitting, combining many trees gives us a more robust and accurate model. Watch as multiple trees appear, each one slightly different from the others. Each tree in the forest is trained on a different bootstrap sample of the data, meaning we randomly sample with replacement from our training set. This technique is called bagging, short for bootstrap aggregating. Each tree makes its own prediction independently. Tree 1 votes for Class A, Tree 2 votes for Class B, Tree 3 votes for Class A again, and so on. The vote badges appear under each tree showing their individual predictions. After all trees have voted, we aggregate their predictions through majority voting for classification or averaging for regression. The arrow points down to the final result box showing that Class A wins with 3 out of 5 votes. Even though individual trees might make mistakes, the majority vote tends to be correct. There's an additional source of randomness in random forests. At each split, we only consider a random subset of features instead of all features. This decorrelates the trees, making their errors more independent. The concept cards explain the 3 key properties. Bagging provides different training sets, feature randomness decorrelates trees, and the combination reduces variance compared to a single tree. This is the wisdom of crowds principle. Many weak learners combine to form one strong learner. Let's wrap up with some key points that frequently come up in FAANG and other technical interviews. The question cards flip in, showing common interview questions you should be prepared to answer. First, explaining Gini versus entropy. Both measure impurity, but Gini is computationally simpler and often preferred, while entropy has information-theoretic foundations. In practice, they usually give similar results. Second, handling missing values. Scikit-learn doesn't natively handle missing values, but you can use imputation or algorithms like XGBoost that have built-in missing value handling. Third, time complexity. Building a tree is O of n times m times log n, where n is samples and m is features. Fourth, preventing overfitting. Use pruning, set max depth, require minimum samples, or use ensemble methods. Fifth, the decision tree versus random forest trade-off. Single trees are more interpretable but less accurate, while random forests are more accurate but less interpretable. Sixth, decision trees can absolutely do regression by averaging target values in leaf nodes instead of taking majority votes. The pros and cons comparison is critical interview material. Pros include high interpretability, no feature scaling required, handling nonlinear relationships, and built-in feature importance. Cons include tendency to overfit, high variance, only access-aligned decision boundaries, and greedy optimization that may miss global optimum. Know when to recommend decision trees: when you need model interpretability in regulated industries, when you have mixed feature types, when you need a quick baseline, or when you want to understand feature importance. If you found this video helpful, please like and subscribe to the AI Engineering channel for more AI engineering content. Thanks for watching.